Hi, everybody. So welcome to the first feature session of the FIB Young session. As you have received in your email, for this year, we suggest to have two periods, to one session, feature session, and the second in-person session in Antibes. So now we have the second session. We'll talk about the open source digital tool for civil engineering. So the moderator will be Nicolas for this session. So I will let him organize the session. So maybe as we are just 10, if you want, you can present yourself in one word and tell if you will be in person in FIB. I don't know if Nicolas agrees with that. So we begin with Nicolas, and then Nicolas, you tell another person to present itself,
Okay.
and you can do the presentation from now.
Okay. Thank you, Yannick, very much, and thank you to the AFGC and the FIB Young Members Group for organizing the session, and then of course for inviting me to moderate. So, my name is Nicola Tosic. I'm an associate professor at the Polytechnic University of Catalonia of construction engineering, and I've been involved with the FIB and actually with the Young Members Group since its initiation in 2017. So it's really a very good environment, dynamic group, and I'm happy that more and more of these kinds of events are organized. So thank you again, Yannick, for the initiative and for the great ideas. And well, I will talk more about the event, but first let's do this round of introduction. No? So I'll go in order of people that I see on the screen. So Yannick has presented himself and myself. So I see Morten, yeah, who will be our speaker, who I should actually present, but Morten, you can introduce yourself briefly now, and I will later more.
Thanks, Nicola. And again, thanks, Yannick, for organizing this session. I really appreciate this. Thanks for inviting me as a speaker. I'm Morten. I will be your speaker today. Truly looking forward to this. I'm a civil engineer from Multiconsult here in Oslo, Norway. I also have a part-time position at the Norwegian University of Science and Technology in Trondheim, Norway, where I do teaching and supervising of students. So in this session, I am here as convener of FIB Task Group 214, and more on the topic in just a couple of minutes.
Yes, thank you, Martin. We actually initially, as you saw in the announcement, Diego Alejandro Talledo was also supposed to be here. Unfortunately, he could not join us, but it will be Martin and myself trying to, let's say, transmit as much information as possible to you. Thank you once more for this quick round of presentations. I think it will make the session more, let's say, familiar to everyone. So saying that we are a kind of very now small closed group, I think we can make it more even interactive and dynamic. So we actually had the round of presentations, but just to say that this is one of the three sessions that will be held. So there is one immediately after this one from 3 to 5, and then there is one tomorrow, right, that you can also attend, that we encourage you. And there will be a kind of follow-up event to this at the Antibes Symposium itself, in one form or the other. We still have to decide whether it will be, again, individual sessions or one large roundtable discussion. But those of you who will attend there, you will have a chance to further even in person directly contribute to the young member group activities. So with that, I'll go to the, let's say, directly to the topic. And again, I want to thank Morten and also Diego for preparing the presentations that you will see today, but that will be given entirely by Morten. On the title of the session is Open Source Digital Tools for Civil Engineering. But let's say the kind of direct motivation for presenting the session is the work carried out within the FIB Task Group 2.14. And actually, the structure of today's event will be such that first we will see a presentation by Morten on FIB Task Group 2.14, and then specifically on the open source Python tool that this group has developed, is maintaining and expanding. So about open source in general, and then about this open source tool, which is the main product of work of this task group. There will also be a demonstration of how to use this tool, how to integrate it with other open source tools. So this will take up about 1 hour, maybe slightly more of our session today, where we have 2 hours. This will then be followed by a kind of moderated discussion between, well, it was initially planned to be me and Morten, but I guess in such a small group, we can make it more open. During his presentation, I would ask you to please just keep your microphones muted, and any questions that come up, write them in the chat. Yannick and I will be monitoring in the sense if there are some technical difficulties and so on. But the question we would wait for after Morten's presentation so that we discuss them kind of in an ordered and structured way. And I think that is it. So we will have about 2 hours until they kick us out and they have to begin Peter's session. So once again, thank you for being here. And I hand it over to Morten, who will share his screen and give us first the presentation and then the demonstration.
Yeah, thanks for the kind introduction, Nicola. Yeah, so again, I'm Morten. I'll be your speaker today. Initially, I also had my good friend and colleague from Task Group 214 with me, so Diego Alejandro Toledo. He could unfortunately not join us today. He had to reschedule his plans, but let's see how we can manage without him. So I'm the convener of Task Group 214. Diego is the co-convener, so we're kind of we're in charge of the development that we're doing in that group. A quick mention of our affiliations. So I'm working at Multiconsult here in Oslo, Norway. I also have a part-time position at NTNU, so the Norwegian University of Science and Technology in Trondheim in Norway. And Diego is associate professor at the IU AV University in Venezia, Italy. So together we've kind of chiseled out this presentation that we wish to call Open Source Digital Tools for Civil Engineering. I'll break this down for you. So we'll discuss a bit what we're doing in Task Group 214. We'll discuss what open source is. So what exactly do we mean when we say open source? We will have a look at options for using open source software in civil engineering. And we will spend a great deal of time exploring how to use this library that we're developing inside Task Group 214. So we will have a look at structural codes. That's the library. We will see how we can integrate that with the open source finite element tool OpenSeas. And we will see how we can automatically generate reports based on Jupyter notebooks by using Mist Markdown. So I'm pretty excited about these topics, so let's go ahead. Well, Task Group 214, we're called Open Source Code Development by the FIB. So that kind of summarizes our objective. We do open source development. We develop and we maintain a Python library. So Python, that's a programming language. I am sure you're all familiar with the language. This library has functionality from different structural design codes. We call the library structural codes, and all the code inside this library is put on GitHub. It's available on GitHub, and it is open source. So what is open source? Especially what is open source software? Well, open source software is basically computer programs or code that is released with a license that allows users to use the software, view and study the source code, modify the source code, and share the original or edited source code. So there are different variants of or different kinds of licenses that you can apply, but basically they are more or less following these four freedoms. So the first one, well, use the software. That might be obvious and trivial. So you can use this software for your purposes. You can view and study the source code. This means that you can actually investigate what happens inside the software. or inside this piece of code when you run it. So you can get a deeper understanding of the working. So you can modify. This means that you can tailor it to your needs, and you can share both the original or the edited source code with others. So these last two are perhaps not so trivial, but they are essential for having an open source community. So summarized, open source lets us build on top of solutions already developed by others, and we can contribute back to help the community progress. And I think this is quite beautiful. So we can collaborate, we can work together, and together we can make things better. Isn't that beautiful? So open source digital tools for civil engineers. What's available to us? Well, I've kind of split the screen into four now. Perhaps arbitrary, but yeah, let's see how we can group some different open source digital tools. In the corner here, we have different tools for data analysis and modeling. So for example, you will find OpenSeas, which is a finite element solver. You have OpenFOAM, which is a CFD solver. You have QGIS, which is a GIS tool. You have FreeCAD, which is a CAD tool. And you have Speckle, which is kind of the backbone for any data-driven design workflow. Next, in this corner, you have the Python ecosystem. So of course you have Python and kind of the core of the language, but you also have all these really strong third-party libraries that are available to us through the Python packaging index, for example. So here exemplified with NumPy and matplotlib, which are for array computations and for visualization and plotting. On the left-hand side here, you have some examples related to how we can use Python code. So Project Jupyter, who's responsible for maintaining Jupyter notebooks, for example. And you have Mist Markdown, which we will go a bit more into later. So Mist Markdown is for generating reports or written content based on your Jupyter notebook. One nice thing that I want to highlight in this corner is that you have the core developers of Python. They are maintaining kind of the backbone of the Python ecosystem. Then you have a lot of third-party libraries and their communities and developers. And you have these kind of attached or loosely attached initiatives represented by Project Jupyter, executable books, and especially this Mist Markdown group, where you have a group of people who are writing code, for example, in TypeScript or JavaScript, that helps us Python developers excel. So you have this glue language and the tools on top of it. In this corner, we have other tools. So we could have called this, well, tools for image or graphic processing. Well, you have GIMP here and Inkscape, which are open source tools for vector graphics and image manipulation. You have Git, which is kind of the de facto standard for source control. And here, VS Code, which is a really good code editor. And this is the one that I will use in the demonstration in just a couple of minutes. Now in the fourth corner, we have structural design. With structural design, I'm referring to the act of taking loads or a structural response and turning this into demands on the structure or checking capacity. In this corner, we have mostly proprietary black boxes. I'm perhaps a bit strict here. So there are initiatives, there are Python libraries, but at the time when we set out to develop structural codes, to our knowledge, there were no kind of major contributors to this box. So what to do? Well, it's kind of problematic that that we have mostly proprietary black boxes. That's because with a black box, only a few people know the inner workings. Bugs can be really hard to detect, and we as users, we need to kind of blindly trust that the developers did as best as they could and that they developed this in accordance to our design codes, for example. So this is why we set out to develop structural codes. And this is what we started 2.5 to 3 years ago. So what is structural codes? Well, it's a library where we have functions covering a significant amount of FIB Model Code 2010 and the current Eurocode 2. So you'll see that there's some dominance of concrete inside of this library. And it's a dominance of kind of the FIB model code and the European code. However, the structure of the library is such that other codes, other national design codes, or other materials could also be covered in principle. So please feel free to reach out if you have code lying around that you would like to contribute related to other codes. We are working on the new FIB model code, so FIB model code 2020, and also on the next generation of Eurocode 2. So we have some code already available inside the library, and we have some open pull requests on GitHub that are under review. We also have the classes, or we have different classes for materials, constitutive laws, geometries, and classes for calculating sectional response. So whereas kind of the design code stuff up here is kind of the foundation for the library, these classes, as we'll see in the demonstration, I believe that these classes are what kind of makes or constitutes the X factor of this library. So this is where we use material from the codes in order to calculate sectional responses, for example. The initial version of structural codes was released September last year. We're continuously updating the library. I think we're on version 047 today. And we actually have some merged PRs into our development branch that has not been released yet. So you should be awaiting a new release in the near future. We don't have any kind of predefined scheduled release timeline. So we release every now and then when we see that there are kind of bug fixes or new features that we want to release right away. The library is published on PyPI, so the Python packaging index. So you can pip install it directly as any other Python library. Just pip install structural codes and you're good to go. And we have around 200 monthly downloads. All right, let's see it in action. So what I want to do now, I will demonstrate to you where to find some code. I will open my terminal to the right here. We will have our VS Code window where we will explore a Jupyter notebook and we'll see what we can do. So first of all, we'll head over to GitHub here. So this text might be a bit small on the top here, but it's the FIB International organization on GitHub. So github.com/fib-international. In here, you'll find at least 2 interesting repositories that you can browse. So the first one is where we have the source code for structural codes. Inside this repo, you will see kind of a familiar repo structure here. You will see some requirements files, some pyproject.toml. You will see some README, a license, and you will see the source code of structural codes. Everything is in here. You should be able to go in, browse it, find any algorithm that you're interested in studying and understanding. So you can use and you can study. You will also see traces of our ongoing work. So inside pull requests here, you will see code that has been submitted that we are reviewing, and we are awaiting kind of final decisions from us as the review team, whether we merge it, so that is we kind of implement it in our code base, or whether it needs further improvements. And we have the issues. So here are kind of open issues or open feature requests that we are or are discussing to work on. As always, you also find this README, which kind of points you in the right directions. This is how we install it. And you have some links to our documentation. Our documentation, you can find it up here. So again, this is a static web page with our manual in it. You have a quick start guide here that I would recommend you to go through. And you have the API reference. So pretty much covering everything that is found inside the library. So for example, for Eurocode 2, 2004, you find material properties for concrete and reinforcement. You find the shear capacity, you find crack width calculations, and creep and shrinkage. And of course, you also have our section calculators that I will demonstrate in just a couple of minutes. The other repo on the FIB International group on GitHub is this one that contains the example code for this session. If you have not yet accessed it, I would recommend you to do so, because in here you will find a notebook, so calculations.ipynb. This is everything that we'll go through today. And this is available to you to clone and use as much as you wish. You can even edit it and base your design workflow on this. So please go ahead and explore it. You have this contents. In here, you will also see that I have included a guide on how to use the example. So a couple of ideas on how to kind of browse through the example, kind of in an increasing level of complexity, so to say. And we have this section at the bottom here, where I'm guiding you through installing all dependencies. So let's have a quick look at that before we continue, okay? You see here that there are boxes of what seems to be code, right? So for installing the dependencies, I suggest to use winget, which is the package manager for Windows. So all this is developed for Windows, and I leave it up to you if you're on a Linux or Mac platform to kind of adapt this to your needs. So to install Python on Windows, you would either go to python.org, or you can open a terminal and you can say winget install python.python.3.12, for example, in order to get version 3.12. Hit enter and it will install it for you. Next, we need Git. So Git will then access the code on GitHub. And you need some kind of code editor. I'm using Visual Studio Code. I would recommend to use that, or PyCharm, or any other code editor that helps you write good code. So I'm using VS Code, but I'm not forcing anyone to use that. In order to run Mist, that we will use for generating our report, we need to install Node. It's easy with winget. We restart the terminal and we can install Mist, which is kind of it's a Node library. Behind the scenes for running Mist, we also need to have some LaTeX distribution. So I've tried and tested a bunch of different ones. MikTeX seems to be kind of robust and smooth to install. So this is the one that I'm suggesting to my colleagues at least. And MikTeX again depends on Perl. So again, available on Winget. In some cases, MikTeX or Mist needs to convert some figures, some image formats. For that, you need Inkscape and or also ImageMagick. So please make sure that you have the paths to these two executables on your path environment variable. So that would be the dependencies. Some winget installs and you should be good to go. And perhaps you need to set the execution policy if you're on PowerShell, restart the terminal once in a while. But after this, you should be good to go. Next, you need to get the code available on your computer. So I guess most of you are familiar with Git and the clone command. So basically, the clone command takes the code from GitHub and creates a folder on your computer where this code is stored. So I already did that. So in the terminal here, you will see that I'm inside a folder called c:/user/me. So that's my initials, repos, and then the name of this repository. So it's easy to access from inside the terminal, and inside this folder here, you will find the same files as we have here on GitHub. So where were we? Well, we cloned the repo, we navigated into it, and while we are inside this repo, when we are inside this repo, we should create a virtual Python environment. I always recommend people to use virtual environments when working on Python. That's because you get kind of an isolated environment where you install your libraries and dependencies. If something goes wrong, you can always ditch that virtual environment and reinstall it, and it takes just a couple of minutes to do so, so no harm done. On Windows, you can use the Python launcher, which is py, and you can type 3.12, for example, if you have multiple versions installed. -m, venv, and then venv. This will create a virtual environment inside your folder. So if virtual environments are new to you, I encourage you to, for example, Google real Python virtual environment, and you'll find a good tutorial on real Python on virtual environments. I would recommend going through this one if you're new to the topic. So having created it, we need to activate it. Now we see in my terminal, it tells me that I have activated an environment. After activating it, we need to install the dependencies. The dependencies are given in this requirements.txt file. So this file contains kind of the basic libraries that we need to install to get this example up and running. So you see structural codes, you see matplotlib, OpenSeaSpy, and OpsVis, which is kind of a visualization tool for OpenSeas. You also have IPyKernel, MB format, and Jupyter Server, which are related to running Jupyter notebooks and also to running Mist. So in order to install this, we simply type py-m pip install-r requirements.txt pip, which is the package installation program for Python, helps us installing all these packages, and we should be good to go. So that was kind of a quick walkthrough of how to get set up. Next we'll do is to browse the example. So what can we get out of this example? Well, in order to do so, I have created some tagged commits in the commit history on this repo. So we can do a git list, git log one line graph. You will have an overview over some tagged commits here. First, we will check out is the basic structural codes tag. I will also open Visual Studio Code. So I type code and then a space and a period. And this window shows up. So let's see now. In order to check out this tagged commit, I can simply copy this text here from GitHub, paste it, hit enter, and then my folder structure here resembles that of the tagged commit. So let's explore this notebook together. A notebook, for those of you who are not familiar with that, is a file where you have cells. So this is a cell, this is a cell, this is a cell. Inside these cells, you can write code, so Python code, for example, or you can write plain text, or perhaps also markdown text. So markdown, that's a kind of a text format. Inside this textbook, at this stage, you only have Python code. So in this first cell, you have different imports that are necessary for the example. You see that we are importing NumPy. We are importing some functions from different subpackages of structural codes. And we are importing some classes. We'll have a look at those. We're also importing the Eurocode 2 from structural codes. So this we will access different functions from later. So we can run this cell by simply clicking the play button here, or Control Enter, or Shift Enter if you may. In the next cell here, we are setting the active design code. So we are setting Eurocode 2 2004. We are providing some properties for concrete. So a characteristic cylinder strength, the alpha CC factor, and the partial factor for concrete. And we create a concrete object. Okay, what is this? So the concrete object, let's inspect that one. Concrete, this is a material object. So when we provide FCK equals 35 to this one, we will have available to us all the material properties related to a concrete C35. We can explore those by simply typing and running the cell. We also have a constitutive law, which by default is the parabola rectangle law, which has some properties. You have, for example, a get stress method on the constitutive law, so you can provide a strain and get the stress. Or you have the get tangent or get secant method, so provide a strain and get a tangent modulus or a secant modulus corresponding to that strain. So these material objects, they are kind of the natural starting point when building your notebook based on structural codes. So the concrete object here is some material object with these properties. The same we have for the reinforcement. So we have a factory function here for creating a reinforcement object. So it should be no surprise really that reinforcement is now a reinforcement related to Eurocode 2 2004 with a characteristic strength of 500, design yield strength of 434 4.8, etc. So now we have our material objects. Next, in this cell, we create a geometry and we create a section. So in structural codes, we have the notion of geometries. A geometry is kind of a polygon with some material attached to it. If you add several of these polygons, you get a compound geometry, which can kind of model some arbitrary shaped section. And you can even add arbitrary reinforcement to this compound geometry. In general, you have the surface geometry class, but we also have these more, say, simplified wrapper classes. So one for rectangular geometry and one for circular geometry. So this class, or this call to this constructor, returns a rectangular geometry with a width equals 300 and a height equal to 450 with the material concrete that we created up here. Next, we place reinforcement. So we place 3 bars with diameter 16 at the bottom and the top. So we loop through 2 layers, or say two depths in our cross section. And we use the add reinforcement line function inside structural codes. After doing this, we can use the built-in SVG function of the geometry class to visualize this geometry inside the notebook. So indeed here we see that we have some rectangular section. We have 3 bars at the bottom and 3 bars at the top. Heading back to this final line in this cell, you have a generic section. So whereas the geometry is kind of just the shape and the material of the geometry, the section is a wrapper around this again, and this wrapper exposes several methods that you can use to calculate the sectional response. So we have integrators for integrating the strain response over the cross section, and we have calculators that kind of do various different kinds of integrations. So let's explore that. We can, for example, calculate the moment curvature response. So this simple call to calculate moment curvature on the section calculator on the section, it returns a result object which has different attributes. So you have, for example, the curvature about the y-axis. So that would be the strong axis of this cross section, and the moment about this strong axis. These two are arrays of numbers. So here we have curvatures and the corresponding moments. And of course, these could be visualized, and we will visualize those in just a couple of minutes. So that's one example of what we can do with the section. Let's scroll down here. We can also calculate, for example, interaction domains between axial force and bending, axial force and biaxial bending, or the interaction domain in the kind of biaxial bending plane for a given axial force. So that's given through this call. And the result object here has, well, it has some moments, and you have the axial force, for example. So you have an array of moments, and you have an array of axial forces. So this could also be visualized in some figure. Before doing that, let's also have a look at the topic of calculating, for example, shrinkage according to Eurocode 2. So in this cell, we provide some input to typical shrinkage calculations. So a cement class, we are calculating some area and circumference for drying based on the section that we just that we just defined. We set some properties related to time and define some ambient conditions. So shrinkage has two components. So you have the basic or autogeneous shrinkage and you have the drying shrinkage. In the formulas that we have implemented as functions inside structural codes, we have one function for each equation in the design code. Might sound trivial, but yeah, we do it like that. So we try to implement everything as close as possible to one with the design code. So for calculating the basic or autogeneous shrinkage, we need to calculate this beta AS, which is kind of the time development for the shrinkage, and this final value of the shrinkage. Now, this here function now returns an array of autogeneous shrinkage as a function of time. Next here, we do the same just for drying shrinkage. There we have a couple of more equations. So we need to calculate this time development. We need to calculate some factor related to the thickness of the section. And we have kind of the final drying shrinkage, the final value of the drying shrinkage. So all these are functions that are available inside structural codes. So these function calls are what's necessary for calculating the total shrinkage as a function of time for this given input. Finally,
Martin, sorry, I will take advantage of the privilege of being the moderator just to ask one question. When printing this array of shrinkage, how is the increment determined? Or let's see, what is the...
That's a good question. Well, we are using NumPy here, and we are using the linspace function that's exposed in the NumPy library. So this function takes 3 arguments. So you have the starting point, you have the final point, and the number of points. So here we say we wish to go for 30 years. So that's kind of the final value. And perhaps a rather arbitrary number here. So 300 points in time. Related to this, we have we are always trying to write our functions so that you could either provide a scalar, so one single float, for example, or a NumPy array as input. Especially when it comes to time-dependent properties, I think this is really important. So you'll see here now that this T, that's a array, that's a NumPy array, which is input to the beta AS function. So here we have an array as input, and then you will get an array as output. So an array of beta AS values. And finally here we calculate kind of key figures from these arrays. So the maximum number after 30 years. Takes about no time to run it, and we can do a shrinkage total final. So that would be 0.4 times 10 to the power of -3. So a good guiding number here. All right, so that's the basic features here. I wish to kind of draw your attention to the different levels of the hierarchy. So one level is this representation of design code equations, which we're trying to do as close to one as possible. If you wish to explore it, you can simply control-click on this one, and you will be directed directly into the source code of the library. because you have it available on your computer while you're running it. Next thing I want to highlight is this hierarchy of the materials and the geometry and the section. So having defined your materials from the start, you have a really good starting point for extracting properties. So any property related to your concrete class, for example, should be available to you inside the concrete object. If you have the concrete and the reinforcement object, you can put these inside geometries, and you can put the geometry inside a section, and you should be good to go calculating either moment curvatures or your gross properties of the section. Yeah, gross properties. Why didn't we say that? Well, beamsec.gross properties. Well, we can even do a print of that one. Well, here you have the gross properties of the section. So we have the second area moment about the centroid. You even have some bending strength. Sorry, not strength, but your bending stiffness. Yeah, total area, etc. I also mentioned that we're covering mostly concrete stuff here. A hidden gem is perhaps to have a look at the steel sections that we have available. So we can do from structural codes dot geometry import, for example, sorry, that was me, from. So like this, we import HE, for example. So this is a HE, for example, A section. Now I'm talking about steel sections. So we can do he.profiles to list all the available profiles that we have in here. Let's see now. Let's do an HEA 500. So we simply type this. Now our he.polygon looks like this. This is included for free. We can do a dot area to get the area. We could do IY to get the second area moment about the strong axis, etc. You have various different geometries predefined in here, so feel free to explore this. Now, next topic in this example is to have a look at how to visualize what we just calculated using matplotlib. In order to get to that point, we first need to discard all the changes that we did to our notebook. So once again, I was a bit fast. This is where we were. So I'm clicking the source control tab on the left-hand side here, locating the file calculations.ipynb. And I'm clicking this curly arrow here, which says discard changes. And then discard the changes. Now, if we head over or head back to our terminal, we can do a git checkout integrate matplotlib and our notebook updates. Let me also point to the README file in the repo. So we went through this part, the basic features of structural codes. Now we're in this part. So now we'll just see how we can create some figures, some plots of the response that we just calculated. Let's see what changed. Well, in the first cell, we imported matplotlib.pyplot as PLT. So this is kind of a standard way of importing pyplot. So pyplot, that's a subpackage of matplotlib for creating visualizations. Next thing we will notice here is that in this cell, we again, we're using the np.linspace function to create an array of strains. So these are arrays of the strains of concrete, so the concrete strains. We are asking the constitutive law about ultimate strains. So this get ultimate strain method, it returns two values. So one ultimate strain in compression and one in tension. So the first one, that would be index 0, that would be our ultimate compressive strain for this constitutive law. So we are creating a linearly spaced array from that strain up to 0, and rather arbitrarily again, we're using 100 points. So strains, that's an array of strains. Stresses concrete, well, here we're using the constitutive law and the get stress method, and we're passing the strains to this one. So the stresses, that should be the stresses corresponding to those strains. Next, we're using this plt.subplots function that's defined in the pyplot library. I think this is a quick and easy way to create a figure object and an axis object. So in matplotlib, the figure object is kind of the encapsulating object. That's kind of your visualization. And the axis object, that's kind of one part of your plot. So if you have several subplots, you will have several axis objects. In this case, we just called it without arguments, so we'll have just one subplot, and therefore also only one axis object. This axis object has a plot method where we provide the x values and the y values, so the values along the horizontal axis and the vertical axis. So no surprise here, we're plotting the stresses versus the strains. Let's rerun the first cells here. And we will see what happens now. Since we're running this inside a notebook, and the axis object is the final thing that's kind of returned from this cell, we immediately see the visualization here. So we set the limits for our axis so that it starts at 0, 0, for example. We set labels for these axes. So we see that we have some megapascal label for the stresses here, and we have the strains without the unit. Well, already here we can use this to quite many things. Well, already here we have a tool for plotting basic constitutive laws for the concrete. What happens if we do, does this work? Constitutive law equals Sargent, for example. Let's see. Well, then we get this non-linear curve from the Eurocode. If we just pass nothing, it will take the default, which is what we had. Then you have the parabola rectangle curve. If we do if we want this for a C45 instead, that should be quite simple. So 25.5, that would be our design strength. Let's revert that one. So we have the stresses and the strains for the concrete. Well, we are also doing that for the reinforcement. So here you have it. You have some bilinear elastic plastic model. Remember, we also did our geometry and the section. We calculated our moment curvature relation. Looks like this. So now you have the moment and you have the curvature, and you see this is a typically under-reinforced cross-section where you have the distinct yield point and the ultimate point over here to the right. Since we have no tension or tensile capacity inside or defined in these constitutive laws, we are directly along a cracked stiffness or say a cracked behavior of the cross section. When it comes to shrinkage, we simply plot the various components here. So we have the basic shrinkage, you have the drying shrinkage, or the total shrinkage, and the difference here would be the drying shrinkage. Having this available to you, you could kind of easily see effects of adjusting different numbers here. So going from low to high relative humidity, for example, see the effect of that. And finally, down here, we had the interaction domain between axial force and bending moment. Yeah, note that the vertical axis here is inverted, so the positive numbers, they are in compression. So due to this minus here. So this should make it evident that plotting results from structural codes is quite straightforward when you have matplotlib available to us. Next, let's have a look at OpenSeas. So we need to discard some changes here. And check out integrate OpenSeas. So first of all, OpenSeas, it's an open source finite element software. I think the kind of the background of this tool is an initiative to create an open source tool to do earthquake engineering. But basically, it's a general solver with a lot of options. Originally, I think the required input to it was written in Tcl, but you have the OpenSys Pi library, which kind of exposes a Python API to the software as well. And that's what we will be using here. So still all from inside the notebook, we are now importing these two libraries. So we're importing OpenSysPy.OpenSys as ops, and we're importing opsvis, which is the visualization tool, as opsv. So from these two namespaces, we will have available to us different methods that we will use to kind of invoke OpenSys in the background. So let's have a look at what changed now in our file. Well, we still had our materials. Let's just collapse that one. Constitutive laws that we plotted. Nothing new here. We had our sections. Now we created not just a beam section, but also a column section. So imagine now that we want to analyze a portal frame. So a plane frame with two columns and a beam on the top. So the beam on the top, that would be the one that we already created. The columns on the side, they will have this cross-section. So yeah, never mind the apparent difference in width here, but the width of the beam should be the same as the width of the columns. So we kind of have a continuous plane frame here. So we added the column geometry of the column sections. We still had our moment curvature, our shrinkage that we plotted. And now we come to the interesting stuff related to OpenSys. So I will not go into detail at all when it comes to what we're doing here, but as best as possible, I've commented the code, so you should be able to see what happens. If you find it interesting and you wish to go further into this, I would recommend you to go into our README, click this link, OpenSys link, and you will find the full documentation of OpenSys Pi here. So it's open source. All right, so we create a frame where you have a length of the beam on the top equal to 4.5 meters or 4,500 millimeters, and a height of the columns equal to 3,000 millimeters, so 3 meters. And we apply a distributed vertical load on the beam with an intensity of 20, so that would be Newton per millimeter or kilonewton per meter. We create nodes, we provide boundary conditions, and we are creating some beam and column section. This is where structural codes kind of enters into the picture. So this is a quite simple integration that we're doing here. So we're just providing input to these sections. So we create one section where we provide the stiffness from the concrete, and we provide the area and the second moment of area of the beam section. So that would be the gross area and the gross second moment of area. We do the same for the column section. Next, we define our beam element and beam elements and the column elements. And we can immediately plot the model. Okay, so here we see, well, we have our columns, one to the left, one to the right. We have our beam elements in the middle here. The numbering, well, we see the node numbers and we see the beam numbers. So, the element numbers. These squares at the bottom, they indicate the boundary conditions. So squares indicate that they're fixed. A triangle would indicate that they are simply supported. Next, we provide some load and we plot the load. So here we see that we have the vertical distributed load on the beam. So even with the intensity given here. In this cell, we set up the analysis and we perform a static linear analysis of this system. We plot the deformations. Again, no surprise that this is the deformation that we get. But I think it's quite remarkable that we can do all this from within one notebook. It's blazingly fast, basically because we have so few elements and the system is so simple. But we can do everything from Python inside the Jupyter notebook without any need for third-party black boxes. Furthermore, let's plot the axial force distribution, bending moment distribution, and the shear force distribution. You might notice here that the units of these sectional responses, or the sectional forces, they are consistent with the input units. So if we had provided the input in, say, kilopascal and meters, then we would have had kilonewtons instead. But we provided everything in megapascal and millimeters. So that's why we got Newton and Newton millimeters. Finally, we also included the interaction domain for the column section here. So in this stage of the notebook, we used our sections to provide input to OpenSeas. Well, you could also think of other options here. So let's say you wanted to perform a kind of a stepwise nonlinear analysis. You could also interrupt OpenSeas, then change material behavior depending on the response that you had recorded, etc. All from within this Jupyter notebook. But this is perhaps the simplest way to interact with the system. Right, let's also have a look at how to check the response. So kind of verify the capacities of our sections. That will be the final tagged version here before we go into the mist space. So git checkout capacity control. All that's changed between the previous stage and this one is that we are extracting our element response. So the axial force and the nodal bending moments from our elements. And we are plotting these inside our axial force bending moment interaction diagrams. So here we immediately see the response from the analysis, and we plot them inside the interaction diagram, and we can kind of verify the capacity immediately from this. This is for the column, so base section and top section, and this is for the beam, so the midspan and at the support. Okay. Now, the final thing that I wanted to demonstrate in this session is something, well, slightly different from what we have been doing now. We will generate a report based on this. So if we're doing that, let's git checkout main. So that would be the tip of the main branch. Now we see some quite big changes to our notebook. So let's scroll to the top now and see what happens here. Well, first of all, we have all these markdown cells. And we got this mist.yaml file. Okay, let's have a look at these cells now. In this first cell, you have these 3 dashes at the top and the bottom. And between here, you see kind of, you see the front matter of this notebook. So here we have attributes related to the document that you want to export. So you have names of authors, you have the title, you have the date, you have our affiliations, you even have keywords, you have an abstract for the report. You provide some format that you wish to export to, and even a template. In Mist YAML, you set up your Mist project. Let me, while we are on this topic, let me point you in the direction of more information just before you start. So you can click the Mist link in our README. You get to this page. Inside guide here, you will find a lot of material related to authoring. So how to write different stuff, how to use executable contents, how to export websites, etc., etc. And I would like to especially point to this one and the video tutorial here. So this is Rowan Cockett, who demonstrated how to use Mist Markdown inside Jupyter Lab. So this video is a couple of years old, but it's really inspiring to see and shows all the good efforts that are put down into developing this tool. So that's a shout out to the executable books team behind this. Okay, back to our notebook. So we see that we get some markdown cells, and we see that we have some tags added to our Python cells. These tags, they are kind of special input related to Jupyter Notebook cells, and they control how they will appear and how they will be treated by Mist. I will demonstrate that as soon as we have this up and running. So you see now that we have markdown cells, we have these tags. We are writing markdown here and there to get headings. We're still having our plots. So we are using labels to be able to embed our plots directly inside our report. We are writing stuff. We are cross-referencing stuff. We are creating tables. We are creating figures based on our matplotlib figures, etc. So if you want to preview this, head over to the terminal, type mist start -- execute. This will fire up a static site generator, and it will serve this content on a kind of a local development server, which you can access from your browser. So now we see that there's something happening here. You're building some calculations.ipynb. You're starting the book theme. It's a bit slow now, so I'll just kill this and restart it. And as soon as it is running, we will have it available to us at localhost and port 3000. So let's zoom in on this and we'll see what this kind of provides us with. Well, first of all, we recognize the title. We recognize these two guys as being the authors. We have the affiliations. We have the abstract. We have the text here, which was the introduction. Here you see some familiar figures. So these are the matplotlib figures that we just created. You see the table here. This table, inside this table, we embedded or inserted values of our parameters that we already defined in Python. So meaning if I update now FCK to 45 here, which was the input to my calculations, and I save it, we see behind the scenes here that Jupyter is restarting. It's executing the notebook once again. It's restarting the server. And we will see that we have some lag, but we have 45 as the strength. Let's see what happens if we type 1.0 for alpha CC. Well, it should change. Yeah. There always needs to be some lag when you do this live, right? Yeah, so 1.0. So everything is updated based on your input. And let me stress this. I think this is quite awesome that you can embed values from these variables inside text, inside tables, etc., that you have written in Markdown. These figures that we see here, they might seem as kind of, well, you exported some PNG or something and you embedded that, but no. From this cell, you return the figure object, and then Mist kind of handles this figure object and embeds it for you. So if I wish to, say, rerun this for a reinforcement of type B instead, for example, I can simply save here, and then this figure automatically updates. So obviously it's a bit slow here now, but yeah. Where is it? Yeah, so the key now, I would see that this ultimate strain was reduced now from 7.5 to 5. So let's update that to C again. So we're back here. Again, we have the geometries embedded as figures. We have the section response, shrinkage. Well, we are cross-referencing to figures and tables. If you hover over these links, you get a preview to it. You can click it and it automatically kind of scrolls to this figure. Same for the analysis model. All the visualizations from OpenSeas is also available to you. And kind of as a bonus down here, I also did the control of the transfer shear capacity of the beam and column. All this calculated using functions from structural codes. Okay, so having this preview inside your browser, that's really super useful while you are kind of developing your design. Perhaps you wish to bring this up while you're in a call with a client, and the client says, "Well, let's increase the height of the beam to 500." Or maybe the client says, "Well, we cannot have 450. We need to have 400 height for the beam." You can immediately see the effect of it, and together with the client, you can do kind of well-informed decisions. After the meeting, you would like to generate a report. And that's quite straightforward. Well, you could do a mist build calculations.ipynb -- pdf -- execute. Now this will take the same notebook and process it the same way as it did for creating the static website, but now creating a input file for LaTeX, and then exporting a PDF using our LaTeX installation. We can follow the progress here, and I will bring it up as soon as it's done. So it's rendering the PDF. This might take some time when you run it on your computer as well. We can talk while this is running. We can talk a little bit about templates. So for this example, I have used the lay preprint, so a LaTeX preprint template. But there are several templates available that we can simply just plug and play. So I'll demonstrate this to you in a minute. The export here goes a bit slow, so I'll also leave it up to you to explore with this. So explore different options. So kind of just finalize this example by bringing up the PDF as soon as it's ready from the export. So we can open this, for example, in Sumatra PDF, which is a non-blocking PDF viewer. Oh, yeah, so many projects open now. The formatting is perhaps a bit off in this view. Well, the tables ended up at the top here, but I'm pretty confident that you'll be able to modify this based on your needs. So what you see here is a document that's directly exported from our notebook. You have the title here, you have the authors, you have the affiliations, pretty printed. You have the abstract, some introduction. You get the tables. Every cross-reference is as it should be. Figures are available to you. You have several more tables. You have the sections. And you have the analysis model even, and the results. At the end here, you see some examples of references that we can enter into this, which is also quite neat. So you can simply add the DOI reference, and Mist will handle the rest. So everything that I needed to do to get this nice reference here was to provide the DOI. So to conclude this example, I would like to draw your attention to this conclusion here. So the Python ecosystem contains a range of open source tools that are proven to be extremely useful for the engineering community. Now it's time to make use of them. And with that, my demonstration concludes.
Thank you, Morten. Really
Thank you.
amazing. I think I need a few minutes to wrap my head around everything that I just saw. But really, really huge congratulations to you and Diego and everyone else that worked on it.
Thank you.
For me, it's really, really impressive. At least there are some things I see for the first time. Really impressive. Really, congratulations.
Thank you.
I
If I
think
may, before
yes.
any question, I would really like to kind of put the spotlight on some other contributors here as well. So you mentioned Diego. I also mentioned Diego, a good friend of mine and co-convener of Task Group 214. Let's also send a couple of thoughts to the library maintainers and the core developers of the Python ecosystem. Without them, this could not have been possible. You also have Project Jupyter and executable books, and especially the Mist Markdown group. Big shout out to them. Incredible work they've done. You also have the OpenSeas community. I think their development goes way back. And then finally, you have the FIB. So without the kind of expert networking job that David, Secretary General, is doing, we would not have had the task group up and running. So thank you, David. Really appreciate that. And when we go to GitHub and FIB International, go to structural codes. Over to the right here, you see the list of contributors. So this is not a single person work. Here you have a lot of people contributing and still more to come. So all hands to you. Thank you.
Thank you. Of course, it's understood that it's a team effort, and of course that you built on, as you said, an ecosystem that goes way beyond. So thank you also for mentioning that. So we can go about this in several ways since we are not so many. There are some people who joined in the meantime, and to them I just wrote that you can write your questions in the chat, but also we can have a turn of questions, just raising your hand, and then we will give you, let's say, the word to speak. I will start with the two comments or questions that are currently in the chat, and then in the meantime, I will wait for interventions of others. I can pose some of the questions that I have. There is a congratulations from Peter on this impressive work and team performance.
Thanks, Peter.
We wish you also, Peter, a very successful session that you will have now soon in half an hour. There is one question from Wali, and this is, have you tried to play around with some next-gen Python notebooks such as Marimo?
That's a brilliant question. I've heard about Marimo and it sounds really interesting. I've not explored it yet, but definitely that's on my list.
Okay.
So, but thanks for bringing it up
and
putting it up on my list again. I will definitely check it out.
Okay, as I said, so please everyone just feel free to either type the questions or raise your hand. In the meantime, I'll go ahead with some of the questions that I have, and I'll interrupt I give priority to the questions from the audience once they appear. So there are, let's say, several aspects that I would like to actually address here. There is maybe some more technical ones about what we now saw, which are maybe, let's say, interesting to several audience members. And then there are more kind of global ones about the task group, the philosophy behind the tool, its future, and also a kind of call to action. So maybe as we are now in the more technical aspect and have it more fresh from the presentation, we saw here some demonstrations, but there were also the tags that you showed that there were some, I think, punching shear and so on. So it contains all the provisions from a code. My question there would be, maybe they are misplaced, but kind of reinforcement sizing is something that can be done through this tool, or it's more, let's say, capacity checks of defined elements and sections.
Yeah, that's a good question. Well, you can think of what we implemented so far as being tools to calculate the capacity. So
Okay.
in order to kind of do the sizing, you could either do a manual iteration, so simply just extending the geometry and adding more reinforcement, or you could add some optimization tool. And for that, I guess you could explore, for example, SciPy Optimize, the SciPy Optimize library, which contains a lot of different useful tools for that, and kind of let that massage your different properties.
Okay. Okay.
Mm,
Thank you. We got a question. No, sorry,
mm.
two questions. One is from Filippo. Thanks to the contributors for developing this, and thanks, Morten, for the presentation. What other features, see the entire text, what other feature, I can't see the entire text written. From Eurocode 2, are you guys planning to include in the next versions of structural codes?
Yeah. For the moment, we are not developing much related to the current Eurocode 2, but we're always happy to accept new contributions. So I can briefly mention from the top of my head something that I know that's missing. We should have had something related to time-dependent property development. So we have creep, we have shrinkage, but strength and stiffness development, so far we didn't implement that. So I would really love to accept such contributions. Punching share, as you mentioned, Nicola, it's not in there yet. Please reach out if you wish to contribute that. We also have bond or anchorage of reinforcement that would have been nice to have available as checks. And finally, perhaps the material related to second order effects, which might be quite elaborate to go through and would be a nice contribution to the library. Of course,
Yeah.
I think for the next generation Eurocode 2, I think we have more kind of implemented already in pull requests. So there it's more about reviewing it all. So we're in a process of reviewing it. Yeah.
Okay, I think this ties into the second question that's again by Muad, and this is, have you also implemented pre-stressing to also cover post-tension or pre-stressed sections?
Yeah, thanks. That's also a really good question. So we have been discussing pre-stressing in our meetings. We haven't prioritized it yet, basically. And I mean, it would be a really nice feature to have in there because I think we have the infrastructure ready for handling it. We have the material classes, we have the geometries. So we could, for example, have a property of the reinforcement geometries saying that this should have some pre-strain, for example. Of course, the picture is a bit more complicated, but I will be really happy to see contributions related to this. So please go ahead if you see that you have something to contribute there, Maud.
Thank you. I have two maybe more these kind of technical questions. One would be, is there an option, or how would be done a kind of parametric analysis or a kind of batch analysis of defining some variable as a parameter and then feeding from an Excel or whichever other way and doing this kind of study?
Yeah. How could we do that? Well, that's a good question. Well, so one thing that we might be interested in doing then is perhaps to say, let's say if you have your EC2 2004 and you have our VRDC, which is the concrete shear capacity. So this function takes a range of different inputs. So we could have FCK, you have the depth of the cross-section, the reinforcement amount, etc. Now, on beforehand, we might do a depth equals lin space, say 200 to 700 with a spacing of 50, for example. And perhaps we do a ASL equals NP in space. Let that go from 3 times say 3 bars diameter 12 to, well, just to pick a number, 3 bars diameter 18. Sorry, 18. And then 50 realizations of that. We could then, for example, do a double for loop just to do some primitive calculation here. So looping over all of them and then calculating the shear capacity for combinations of depths and reinforcement areas, and then setting all other properties. While we're doing that, we could store the results, say, in arrays or inside a pandas data frame, for example. Then we would get kind of a whole lot of realizations of this shear capacity for all the different combinations of input parameters. So does that kind of at least slightly touch upon what you're thinking about, Nicola?
Yeah, just exactly these ways of how we could do kind of batch analysis or some parametric, and I guess for sure there will be ways also to linking it with some pre-prepared file where I already do like this discretization of depths and so on.
Sure. And one thing related to this perhaps is to, well, now we've focused a bit, or we've focused mainly on kind of the designer, so the engineering side of this. And perhaps this could be a bit more related to kind of the scientific side.
Yeah.
So say perhaps this VRDC function could be kind of stripped down so that you have kind of all your exponents and your factors as free variables. Then you might wish to collect a range of experimental results and perhaps fit those properties or those factors and exponents based on your experimental results. So that should be possible based on what we already have in structural codes. Or you could run through all the input from those benchmark experiments that you had gathered and then assess kind of the uncertainty of the code equation.
Exactly, that was in line of my second question, and this is, yeah, from my perspective, is more from the research part. So for code development, this would be important and interesting. And sometimes, yes, we want to check these code equations against databases of experimental results. But when we do that, of course, we are operating with kind of observed or measured values. So, of course, we declare partial factors as one, but we also want to operate with average and not characteristic values, for example.
Yeah, that's a good point.
That would require entering into the code and changing something, because I saw in screen, of course, the gamma C can be defined, but the FCK FCM relation, I guess that goes maybe deeper, or I would have to take care and adjust that actually I enter what I measured minus 8 megapascals so that I have the code operate. Yeah.
Yeah, or well, I guess that depends on how you kind of interpret this equation then. So if FCK is kind of, is this really the lower fractile that you're entering, or is it just some representative number?
Yeah.
So if this is actually the lower 5% fractile, then you should subtract 8 from your measurement. If it's just some representative number, why not use the measurement directly in it? Yeah. And then, of course, the gamma C should be 1.0. Yeah, that's a good point.
We have another question.
Okay, great.
From the presentation, the focus seemed to be on visualizations of the section, some of its properties, etc. Have you thought of the addition of the engineering formulas to let the reader follow through the procedure, much like a traditional hand calculation? It would be kind of self-explainable, like these self-explainable AIs. Like now I am taking this equation, now I'm plotting this. So that's the
Yeah,
question.
I really like that question. And you have, I would like to kind of draw the attention to a complementary tool here. So you can do Python hand calcs. This is a really powerful tool by Connor Firster. So it allows you to render your Python code as math. So rendering your Python code as hand calculations. This is really strong. We haven't really explored how to kind of integrate these tools yet, but I know that some or many of my colleagues they're using hand calcs in their current reports. So when they're writing reports in Jupyter Notebooks, they're using hand calcs. So this kind of serves what you're asking here. It would be great to explore how to kind of integrate those two APIs, so to say, because it would make it even more transparent and even more applicable to entering directly into a notebook. If you are interested in exploring this, please reach out and let me know how it goes. I'll be happy to discuss it later.
Thank you. I hope that addresses one's question. There are no other new ones, so then I could a bit shift the conversation and maybe ask the question. So since you are here now really going into that kind of nitty-gritty of the design codes and really having to work through all the loops of the calculations that are there, this can also be, I think, a valuable tool of finding some, let's say, inconsistencies, or let's say problems in definitions in the design code within the FIB. Do you have, through the task group, let's say, liaison with other groups that are really developing the models for shear, punching, deflection, whatever, that you have the freedom to come to them and say, we are implementing this, we actually see that following these clauses. Okay, since I can record to my computer, then he can merge the files, hopefully.
Very good. Yeah, well, at least I think there's two sides of that question. So in FIB, we have a separate task group for developing examples from the model code. We are liaising with that one. So our goal there is to assist that group in creating kind of digital versions of their examples. And I guess for that, we will use Jupyter Notebooks. Second is that we have some connection to the Eurocodes at least. So at least one of our members is a key contributor to the development of the Eurocodes. For the moment, we don't really have a strong feedback into that development. But of course, we're following the development closely while implementing the models from the new Eurocode. And from that, we might actually uncover something that was unforeseen while developing those codes.
And when receiving, for example, these push requests from, let's say, people to include perhaps new contributors outside the group, that will include new modules that you don't have until now. For example, you will, let's say, encourage people to work on punching, so on. In reviewing this, are you then also leaning into the other task groups for helping you to, let's say, interpret properly what people are doing, or is this within the task group?
We actually didn't do that so far. So far, we have kind of leaned much on ourselves, kind of. So basically, we are, sorry, I'm in the wrong repo here. So if we get a pull request related to something, well, for example, image data cracking, according to model code 2020, we go through all the code and we look for inconsistencies with the model code. We also look for kind of coding inconsistencies. So is the Python code as it is written now, does that follow kind of our style guide? But yeah, it's two sides to that. We'll both look at the style guide and also on the consistency with the design code. Definitely when we run into issues, we should lean on those who develop the code. So yeah, reaching out across different task groups.
And you mentioned, for example, 200 downloads a month, which to me seems like a really impressive statistic. Do
No,
you
thank you.
have any idea about the, let's say, users, use cases, if they are more research, more industry, within the FIB? Do you have any information on that?
No, not really. Well, from time to time, I get or people reach out on LinkedIn to kind of ask questions about use cases. We have the guys over at Strukturelle in Denmark. They created a Python web application based on structural codes. So I would guess that some of those downloads are related to their continuous integration pipeline as well. But I would guess the main application area for the moment is design offices.
Okay. Yeah, it definitely seems so. So because let's say in the audience we saw that we have people from Arrow, also from company where you work, but also researchers. What would be, let's say, your one main argument to the people who are in the design offices to really use this tool instead of, well, there are kind of no others, but also then on the research side. So kind of what would be your selling point, I think, it's strongest for the tool.
I think my main
Not that
selling,
you are selling, it's open source, of course, but let's say.
well, if we can call it my main free for all point then, if not selling.
Yeah.
Well, my main point here is that this could then serve as kind of the the benchmark for the industry. So this is where we find our design equations, and this is where we find our algorithms for calculating our bending responses. And we kind of use this as a library where we can agree upon different methods. Everyone can use the same. We can even share notebooks with each other. We can contribute to improving the methods of our community. And I briefly mentioned in the beginning that on this side of the equation, we mainly rely on proprietary black boxes. If we instead start relying on tools like this, we kind of democratize the community and we help each other improve as well. So I think there's a lot of pros to this.
And what, if I may ask, kind of what started you on this journey, and was it a kind of journey from zero? Of course, Python existed, Jupyter, all this ecosystem existed, but was there anything to the codes that you built upon, or what motivated you? Because to me, it seems a very kind of selfless effort. Because of course, I'm sure that companies have similar things internally, but then they are, let's say, for commercial purposes internal and not really shared. So this is, yeah, very altruistic way. So can you explain a bit the background? And with that, I want to make introduction into the, let's say, how others can follow you on that route.
I think the main motivation is related to this kind of the missing piece of the puzzle that I showed in one of the slides. So some years ago, I was busy developing some other Python tools internally here. I also realized that there's kind of a drift towards open source tools in a lot of other communities and other industries, but not in our community. And I thought the FIB is so open and sharing, and we have this kind of the spirit of being some bridge between research and practice and sharing our knowledge in order to improve the built society. So I figured perhaps a Python library could be a good way to strengthen this dissemination of the knowledge from research to practice, but also between practitioners. So I won't say that kind of I had some idea, but at least I pitched it to someone who thought it was a good idea, and then we built upon that. So creating some library that could serve as this role model was perhaps the main motivation.
And just to, let's say, close up, could
Mm,
you tell us, please, a bit more about briefly about the task group, so your kind of inner dynamic,
mm,
and how people here or their colleagues could get involved, because we had some very nice comments, and I think everybody's very interested, and
mm,
there are potential new members. So how does
sure.
task group 2.14 operate, and how will it maintain these two?
Yeah, so first of all, let's just make it clear that you really don't need to be part of the task group to contribute. So we have, I would guess that 2/3 of the contributors on GitHub, they are from the task group. The rest are from outside. So perhaps master students or externals that have reached out with suggestions. So if you have limited time and only want to contribute Python, please reach out and we can find some way to contribute there. If you wish to be part of the task group, please also reach out about that. We are welcoming new members. We do have, say, 9 to 10 online meetings per year. We will have our first really informal in-person meeting now in Antibes. So I'm really looking forward to that. Although Diego and I have had one in-person meeting from before, that's a couple of years ago. But yeah, apart from that, only digital online meetings. The way we are working, we have our meetings where we discuss new features, update each other, and then everything else goes through pull requests and issues on GitHub. Um, some of us do some correspondence on WhatsApp also, or by email. Um, but yeah, very little traveling and very little talk and much more doing. Let's let's put it that way.
So really, I hope that people will take away from this that they can get involved
Yeah, please.
from small steps to, let's say, more involvement. And uh, you have, I mean, you can even find the access form to the task group online, but you also have more test contacts. So please feel free to reach out. I just want to find a curiosity. Did you um, ever talk to Michael Scott from, let's say, who is maintaining OpenSeas?
No, I didn't, but I guess Diego is familiar with Michael. Diego has contributed code to OpenSeas from before, so that part of the demonstration is kind of Diego's baby.
I'm asking because we had Michael as a kind of presenting a webinar for the FIB young members, and I also interacted him when uploading some code. But I think he could have, I think, interesting advice and maybe cautionary tales about open source tools in civil engineering. So I think it would be useful to listen to him and his experience, because with Frank, well, now it's Michael, but I think with one postdoc recently that they are maintaining OpenSeas.
Hmm.
Hopefully this can, let's say, collaboration continue.
Oh, thank you. That's a good idea. I'll see how we can kind of how we can interact then. Uh,
So
thanks.
really, thank you so much, and I'm really impressed and looking forward to watching several times the recording, because there are things to learn, and I want to try it out, and also with some colleagues.